let's go over the midterm corrections so you guys can get some feedback here. And I'm going to show the common mistakes that you guys did so you don't repeat that for your final exam. And let's start with the first question. Convert the following integers to base 2. So we have here the calculator just to help us as an auxiliary tool so we can validate our answers. Here you're not supposed to use the calculator, you're supposed to do either the division by 2 or the subtraction method. So let's use the division by 2 on this first one. And I'm going to do it over here. So 170 divided by 2, get 85. 0 divided by 2, I get 42. 1 divided by 2, 21. 0 divided by 2, 10 and a half. 1 divided by 2, I get my 5. 0 divided by 2, get my 2. 1 divided by 2, 1, 0, and divided by 2, 0, and 1. Perfect. And now, common mistake, people write 0101 as an answer, but yeah, don't forget that you're reading the values from bottom top approach. So here we get as an answer 1, 2, 3, 4, 1, 2, 3, 4, base 2. And now we're going to see number 2, which is 240. And let's do that one over here. So I get, this is A, let's do B over here. So I get my 240 divided by 2, 120, 0, 2, 60, 0, 2, 30, 0, 2, 15, 0, 2, 7 and a half or 7, 1, 2, 3.5, 1, 2, 1.5, 1, 2, 0, and 1. And I read from this part to here, 1, 1, 1, 4 ones and 4 zeros, base 2. Alright, let's go over question number 2. On question number 2, is important to pay attention here that I'm saying to convert the following hexa number, so we have an hexadecimal number, into a 12-bit binary. So 12-bit binary. So that means that I need to have 12 bits, not 8, not 4, 12 bits. And then I need to indicate on those 12 bits which one is the most significant bit and the least significant bit. So have in mind that yes, you do have the most significant place on an hexa number, but you don't call that most significant bit. When you're talking about bits, these needs to be related with zeros and ones and not the most or the least significant number on an hexa number. So for example, 0 or E is not an answer for your MSB or LSB, or MSB equal to 1 here and LSB equal to A. It's not an answer for that. You need to convert this hexa to binary. Well, we know that converting is easy because this is just grouping sets of 4 bits. So the first one, we have 4 zeros, and then we have 9, which is 8 plus 1, and then we have E, which is 1, 1, 1, and 0. Here you go, I have my 12 bits, and now I just need to indicate which one is the most significant bit and the least significant bit. And the same thing applies for 11A. So 1 is this, and A is 10, so it's 8 plus 2. So most significant bit and least significant bit. Perfect. Let's keep going. Question number 3. How many bits are needed to represent all the upper and lower case characters of the alphabet? So we have 26 uppercase plus 26 lower plus digits from 0 to 9, so 10 digits, plus an addition of 20 punctuations. So if I sum all these, I get 82 82 symbols that I need to represent. So how many bits do I need now for these 82? Well, different ways of approaching this. I think the easiest way is just we know that if we do 2 to the power of the number of bits, we are going to get a number here. And as long as that number is bigger than 82, we're good to go. So by experimentation, if you do 2 to the 6, so if I go here, and let's go in scientific mode, and if I do 2 to the 6, I get 64 symbols, which is not enough to cover 82. So if I do 2 to the 7, I know it's the double, well, let's just use this one, 2 to the 7, 128. So here you go, 7 bits, it's your answer, because it's enough to cover 82 symbols that you have over here. All right, let's keep going. Let's go now for binary arithmetic. This is a question that a lot of people get a little bit confused on what's going on here. So first of all, it's asking for what are the signed and unsigned values of the following binary numbers. So if I have this binary number, when I'm asking a question like this, I would like to know which decimal value is actually this binary representing. So writing an answer with just binary numbers doesn't give me the right answer because I don't know which value it's representing. So the answer needs to be a decimal value. And you're going to have two possible answers for each one of these questions over here. So for A, you're going to have a representation if this, or a value if this number is a signed number, and the value if this number is unsigned. So let's do the unsigned. The unsigned, I pick up this number and I literally just convert it to a decimal value. So I have 3, 4, 5 bits. So this is going to be 1, 2, 4, 8, and 16. It will just make it easier. Actually, I'm going to write that over here. Will make it easier for us to convert this binary number. So I have 16 plus 1. So let's go here for the unsigned value. I have 16 plus 1, which gives me 17. So this number, if it's an unsigned number, no sign, it's representing the value 17 decimal. So I'm going to put here a big D, so we know it's 17. But if it's a signed number, now that means that my most significant bit, this 1 over here, is going to tell me if it's a positive or a negative number. In this case, it's a 1, so it's a negative number. So what I'm going to do is I'm going to apply the first complement of this number so I can reverse it. So if I do that, first complement is just flip the bits, so I get 0, 1, 2, 3, and then 0. This is still in base 2. And now if I convert this is equal to 8 plus 4 plus 2, which is equal to 14. But the value that I'm actually representing is minus 14 because I have that 1 telling me that it's a negative number. So this is the right answer for this question. So if we go for B, we apply exactly the same thing. We need to count all the values, all the numbers here. So common mistake is to ignore this 0 and then assuming that this is a negative number. That's wrong. This number is positive because the most significant bit is a 0. So let's go first with unsigned. So unsigned, it does not matter. Sorry. Unsigned, it does not matter. What I have, it's actually the same thing as above. 8 plus 4 plus 2. So equals to 14, positive 14. But if it's a signed number, my most significant bit, it's a 0, so it's a positive number. So I can put a negative here. It's a positive number, so it's exactly the same number. 8 plus 4 plus 2 equals to 14D. Because it's a positive, I don't need to apply any of this first complement. So let's go over question number 2. It's exactly the same thing as question 1, but now we use the second complement to get the answer from signed numbers. So on your first answer for the first one, if it's unsigned, you have exactly the same answer. 16 plus 1 gives you 17 in decimal. But for your signed number, this is most significant bit is a 1, so this is a negative number. So let's apply the first complement. Couple of ways of doing this. You either apply first complement, add 1, or we can go from the right to the left, find the first one, and then flip the bits. So you get something like this. And if I convert these, now I have the number, I have 8 plus 4 plus 2 plus 1, which is equal to 15, but I'm actually representing the number minus 15 because my most significant bit, again, it's 1. Perfect. So now let's go to B. B is exactly the same answer as your first question. So unsigned, you have 8 plus 4 plus 2 equals to 14D. And for your signed, most significant bit is positive. And here you go. That's your answers. I can highlight here so we can know what's the expected answer. And that's it. So let's keep going. All right, problem number 3, BCD Arithmetic. So common mistake here was to convert these numbers to binary and then do the additions in binary. That's not correct. So you need to convert these numbers to BCD and then do the respective addition. So let's go over the first one. 8, 8 in BCD. So each digit is going to have 4 bits. 8 is going to be 1, 0, 0, 0, and the other 8, 1, 0, 0. And 6 is going to be 0, 0, 1, 0, 0, 1, 1, 0. Sorry, 0, 1, 1, 0, 0, 1, 1, 0. And I'm going to sum these, so I get 0, 1, 1, 1, 0, 1, 1, 1. In BCD, we know that if the result here are letters from A to F, I need to fix by adding 6 to the respective place where I have a letter. So this is the same thing as having E. So what I do is I pick up my EE and I'm going to add the 6, 6. And now let's do the math. 0, 1, 1, 0 goes 1, 1 goes down, 1, 0, 1, 1. And then 0, 1, 1, 1, 0, and 1. All right, and now if I split these in 4, because BCD is 4, I get 1, 5, and 4, 154. That's my answer. All right, let's go down. So 25 is 0, 0, 1, 0, and 5 is 0, 1, 0, 1. 40 is 0, 1, 0, 0, and then 4 zeros. Let's add, and I get the following answer, which is 65. All right. Boolean reduction without using the K-maps. We need to find the minimum cost, stop, and pause. So a lot of people lost points here because you didn't read probably the question properly, but you need to find the stop and the pause, not just the stop or just the pause. And then we need to find the simplest equation. All right, so how do we address these? Different ways. We can use the truth table, get the expressions, or we can get the expressions right away. I'm going to use the truth table here. And how many bits are we going to have here? So I'm going from 0 to 7. So if I use my calculator over here, 2 with 3 bits, I can cover up to 8. So 0 to 7. So 3 bits is more than enough. Perfect. Oh, actually, I was not paying attention, but it's actually stated over here. X1, 2, and 3. So only 3 bits that I'm going to use. All right. So let's put X1, X2, and x3, and this is my output. And now I'm going to teach you a trick to do the truth table without missing any numbers. So here you're going to have eight combinations, and they swap between 0 and 1. So this is the least significant bit, is the one that changes more often. So you get 0 1 0 1 0 1 0 1 8 times, and then this one changes every 2. So 0 0 1 1 0 0 1 1, and then the last one, the most significant bit, is the one that changes the last, and you're going to be 4 zeros and 4 ones. So 0 0 0 0 and 1 1 1 1. Perfect. Okay, now I'm going to write my f, and these are the minimum terms. These are the positions where I have ones. So I'm going to write here, this is m0, sorry, this is m0, m1, m2, m3, m4, m5, m6, and m7. Alright, and I have 0 is 1, 1, 4 is 1, 5 is 1, 6 is 1, and 7 is 1. So I have 0 0 over here. Alright, so let's start with my SOP, and my f is equal to x1, x2, x3 all negated, or x1, x2, x3. So I'm going to write, we have 2, 4, 6 min terms over here. Alright, and I put the negations. So this one is going to be 0 0, this one is going to be 0 0 over here, this one is going to be 0 on x2, then negation on x3, and the last one all ones. Perfect. Alright, let's simplify these ones, see what we can do. Alright, let me pick a different color here, green for example. Alright, these two terms can be together right away, and I get x1, x2 negated. Alright, I'm going to probably put these for now, and then we take care of that. Let's keep going. What else can we find that it's a common term? We can group this one with that one. And so every time, to simplicity, well, let's put it here. Okay, x1, x2, and great. It's this one with this one. And actually I can put also these two together. So let's do that. And I actually forgot to put the plus over here. Alright, let's keep going. And I get x1, x2 with my x3 plus x3. Alright, great. So I know that all of these are going to be equal to 1. I get rid of all those x3s, and I get f equal to x1, x2 negated, or x1, x2 negated, or x1, x2. Alright, let's keep going further because I can still simplify this. The cool part now is that I can put this one together with this one. So these two together. Actually, let me go back to red. Alright, this one, and f is equal to x2 negated, and I can put also these two together with x1 as a common term, so this one, and this is my SOP, the simplest version of my SOP. Alright, it's still not the final answer. I still need to find the pause, so let's go and find the pause. So for my pause, I start with my f negated, and I'm going to look at the zeros. I'm negating my f so I can work with minimum terms instead of max terms, and then simplify the same way that I'm doing here, and then I negate everything to get the right answer. So let's get the zeros. The first one, so I have two terms over here, and the first one is negated 1 and 3, and the other one is negated on 1. Perfect. So pretty cool. I can put these two terms as a common factor, right? Because this is equal to 1. In fact, we can actually indicate that here too. We can just complement this one if we have space, and kind of saying that is all equal to 1. And I get f negated equals to x1, x2, which I need to negate f twice so I can get the right answer. And negating f twice gives you f, and here I applied De Morgan's, and if I apply De Morgan's, I get exactly this. And here you go. We have a SOP and a pause that are exactly the same value, or the same circuit, which doesn't matter which one you pick, you get exactly the same answer, and you find the minimum SOP and pause. All right. Our last question is going to be using K-maps. Consider the circuit below and find the respective truth table and Carnot mapping. So let's find the truth table. See if I can find space over here. And all right, so truth table. I have 4 bits, so I have A, B, C, and D. And I have my F, my output. Okay, same applies here. I'm going to write 16. I got 2, 4, 6, 8, 2, 4, 6, 8. And I do 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Now it goes every 4. And it goes every 8. Perfect. All right, let's put this guy over here. Now that we have our truth table, let's go and fill the values. So if I have all zeros, which is the value that it's over here, all zeros, I get a 1 here. So that means that this F is a 1. Second one here, I get, if I get 0, 0, 0, 1, so 0, 0, 0, 1, I get a 1. Then I have, the next one is this one, 0, 0, 1, 1, which is this. So this is a 0. And then I have 0, 1, 0, 0, 0, 1, 0, 0. Then I have 0, 1, 0, 1, 0, 1, 0, 1. Then I have 0, 1, 1, 0, 0, 1, 1, 0. Then I have 0, 1, 1, 1, 0, 1, 1, 1. Then I have 1, 0, 0, 0, 1, 0, 0, 0. And then I have 1, 0, 0, 1, 1, 0, 0, 1. All the other ones are going to be 0. Alright, wonderful. And let's design the K-map. Alright, for the K-map, we have 4 variables. and I'm going to put AB over here, C and D, 0 0 0 1 1 1 1 0, the gray code, changing one bit at a time. And now I populate my truth table and I get, or my K-map, sorry, 1 1 0 1. So I just put this guy 1 1 0 1. Then I have 1 1 1 1 1 1 1 1. Then I have 1 1 0 0 1 1 0 0, and then 0 0 0 0. Perfect. All right. This is just for demonstration. I'm going to erase the truth table and just use the K-map. Obviously, in your exam, you just go to the next page and keep going. This is the answer for A, where you have the truth table and your K-map. But now, question B is asking for the simplest circuit and design it. So two things, find the simplest and then design it. Simplest means that you need to take, once again, the SOP and the POS, and then see which one is going to be the easier to design. So again, I'm going to delete the truth table, but that's just for me finding space to do the rest of the exercise. You will be doing this on another piece of paper. And let's start with our SOP. In our SOP, what we're doing is we're grouping the ones together. So let's group the ones together here. Let me find, yeah, we can do it this column. All right, so group the ones. We want to maximize the number of ones that we put in groups in powers of 2. So probably the easiest choice is these two together over here. And let's take the expression as we go, so we don't get completely lost. And my F is equal to that one. What it has in common is going to be your A, your B, and that's it, A and B. Okay, let me put the here really quick. Oh, sorry, actually it's going to be A naught. A, B, C, and D. I'm glad that I did this because I now identify the mistake and I can correct here. So A naught, or let's keep grouping. And the next can be, let's group these 4 ones together. Okay, so you can pick and group these 4 ones together, and the expression that I get out of that is going to be an A naught and a D. So it's outside of the A, inside of D, intersect C and B. Perfect. And now I just need to group this one with these ones. So the best way to do is grouping these 2 with these 2 to make 4. All right. So I group these 2 with these 2. And my expression now is going to be B naught and C naught. All right, perfect. Let's design this really quick. So what we have is 3 AND gates connected to my OR gate, and I have my A negated, B, and this A kind of connects with that one, D, and then B and C negated. So if I count the number of gates that I have over here, I get 1, 2, 3, 4, 5, 6, 7 gates using my SOP. All right, let's go over the pause. And the pause, now I'm grouping my zeros. So F, and let's group the zeros. So I get a big chunk of zeros over here, and that's going to be A and B. Or I can group these 4 bits over here, or 4 zeros over here, make a bigger group of 4 of zeros, and this is going to be A and C. And at last I have this 0 alone, but I actually can merge with this 0 on the side. So I can do D0 with D0, and I get B naught, C, and D naught. Alright, great. I know that I need to apply De Morgan's. So what I get is, in fact, something like this. Alright, great. So let's design this one, which we have 3 OR gates there connected to an AND gate. And these two are negated, these two are negated, and this one is only negated in the middle. So if I count the number of gates that I have over here, I get 1, 2, 3, 4. And now notice that I have A negated 5, B negated 6, and C negated 7. 7 gates also for my SOP. You could stop here. I'm okay if this is your answer and you get, it does not matter if you do SOP or pause, you get exactly the same amount of gates. But in fact, the answer is that you can reduce this even a little bit further. Notice that these 2 gates over here are actually NAND gates. So that means that I can reduce 1, 2, and 3, 4, 5 gates just to 2 gates. So if I redesign this circuit over here, and I'm going to do a different color, let me do a brighter color. Let's do orange, see how it goes. You just need to find space now. I'm going to do it here. So in fact, what we have is an AND gate, another NAND gate, and now if I count the number of gates that I have just by doing these, I actually have 1, 2, 3, 4, 5 gates. But that's actually also true over here. I can apply a couple of tricks over here. Notice that this is actually a NOR gate over here. So that means that I get 1, 2, 3, 4, also 5 gates. So if I go up on my circuit and I design with an OR, actually the easiest, the simplest circuit is with 5 gates. Again, I'm okay if you stop at 7 gates as long as you give stop and pause, because you need to check both. You get full credit, otherwise you lose some points. But I hope you learn over this video, and you can recall this video to study for your final exam anytime that you want, and let me know if you have any questions. One more note, if I made a mistake counting your points, if you see that for some reason I didn't count them properly, please contact me. I can make mistakes. I apologize if I do, and I will correct your grade as soon as possible. Thank you.